Hello and welcome. Good morning, good afternoon or good evening, depending on where you're watching from in the world. Thank you for joining us for this IHEAM webinar presented by Thermal Energy International. My name is Victoria Emerton and I'm the Conference Director for Healthcare Estates. Today's webinar will be presented by Gunther Lang, Sales Director for Europe, and Sam Morby, Director of Technology from Thermal Energy International. We're also joined by Walton Dunlop, a heat recovery specialist at Thermal Energy International, who'll be part of the question and answer panel. The title of the presentation is Modernisation of Steam and Hot Water Systems, an Introduction to the Steam and Condensate Loop. We'll be using the questions function to take questions from the audience, and this can be found at the top right-hand side of your screen. It's the icon with a question mark in a speech bubble. We won't have time to use the audience hands up facility, so please post your questions to the organiser, and Gunther, Sam and Walton will answer as many questions as there is time for at the end of the session. If you have questions you prefer our speakers to answer privately at the end, please send these to them via email, details of which will be on the last slide at the end of this presentation. Please note that a certificate of attendance will be sent to all those who watch the live webinar in its entirety, and the recording of this webinar will be available soon after the session ends on the Healthcare Estates website under the webinar tab and also on the IHEAM website. There are 5 handouts that support the content of the presentation, and these are available from the handouts tab in the panel to the right of your screen. They're also available for downloading after the session, and you can also download them during the presentation this morning. Please visit the Healthcare Estates website for information on the other webinars that we're running over the next few weeks, and you'll also be able to find information on IHEAM Digital Week in October and a form to submit content to get involved in that. So I'd like to hand over to Gunther and Sam now. Thank you very much.
Thank you for that introduction, Victoria, and also for everyone for attending today. I hope you find it a valuable use of your time. So as Victoria said, today we're looking at the modernisation of steam and hot water systems within the healthcare estates, and we're going to take a case study-led approach looking at actual applications of different technologies. And as a basis for the presentation, we'll be walking around the steam and condensate loop of a typical hospital. So hopefully this is the reason why you're interested. The NHS is committed to meeting the government's carbon reduction targets, which is an 80% reduction on 1990 carbon emissions by 2050. In fact, the NHS is committed to exceeding these targets. NHS buildings consume over £410 million worth of energy annually and produce 3.7 million tonnes of CO2. So there's a significant amount that can be done within the Estates Department to achieving these goals. The NHS carbon reduction strategy has looked at the most practical measures for reducing CO2 and minimising the investment. This table here shows you the savings by the height of the column in pounds, and the width of the column is the CO2 savings. What you'll notice is that this end is a very high CO2 savings per pound spent. These are really reduction strategies. These are things like reducing wastage of drugs, eliminating transport emissions by having virtual meetings, etc. But then we move on to the efficiency type savings. These are things like the CHP, insulation, boiler upgrades. And the vast majority of these are things that in the Estates Department we can actively participate within. You'll see there are some negative costs. These are emissions that you actually have to pay to reduce. There's no saving, there's no return on investment for those. And typically they are things like biomass, wind turbines, moving away from carbon fossil fuels. A little bit about my background and Thermal Energy's background, why we're qualified, I guess, to be here today. We're experts in the reduction, recovery and use of waste heat. We have over 25 years of experience doing so. And I'm very pleased to say we've worked with over 14 NHS trusts and healthcare facilities in the UK, along with hospitals in North America and Europe. Within the NHS, we've saved over 220,000 tonnes of carbon across the lifetime of our projects installed to date, and that results in around £24 million worth of savings. If I was really to sum up what Thermal Energy do, we specialise in making projects happen. What this means is that we can work with our partners, our customers, to help them identify opportunities, develop them to be an investable business case, help them find funding streams for those particular projects, and then give them a turnkey solution for a fixed price and guaranteed savings, and then even help them with the aftercare of those projects. This slide here shows a Sankey diagram. For those that aren't familiar, a Sankey diagram, the width of the arrow tells, or the width of the line tells you how much energy or how much you're measuring in each line. And this Sankey diagram is showing the total US energy consumption in 2018. It's measured in quads. A quad is a quadrillion, which is 1 with 15 zeros afterwards. It's actually in BTUs, but it doesn't really matter because a BTU is very similar to a kilojoule. What I really wanted to highlight here is if you look at the total energy consumption across the whole of the US, it's 101 quads. 68% of that is rejected energy or waste energy. And this is why the International Energy Agency say that energy efficiency is the hidden fuel. We actually believe it's the first fuel. If we're going to achieve climate reduction goals, then energy efficiency is going to be the primary driver to achieving those goals, because it actually has a return on investment. If we take a more closer look to our individual facilities within the hospitals and the states that we run, this is a Sankey diagram for a typical steam boiler. You can see here there's a considerable opportunity for optimization in an unoptimized system. For 100% fuel, the natural gas or whatever other fuel we're buying, we get typically 55% useful heat output. We're going to talk through how you can recover at least 80% of the energy lost in these boiler plant and steam system operations. I know many facilities are considering decentralization and moving to hot water systems. However, the vast majority of these savings can be achieved through upgrading the existing infrastructure and rationalization. So why do we use steam? I guess the key reason is the high energy content. It typically has 20 times more energy per kilogram than hot water. The reason for this is we're not taking the temperature energy out of the steam, we're using the latent energy which is released from the phase change of steam to water. Steam also has a very neat function in that saturated steam, the temperature is controlled by the pressure. There's a direct relationship, as you can see by this curve. We have relatively high temperatures. It's non-toxic. In fact, we can use steam directly in food products, and we often also use it for humidification purposes, directly injecting it into HVAC systems to humidify the air. Steam also travels under its own pressure. There's no requirement for pumps. As long as you maintain the pressure, it will also achieve a relatively constant temperature. So unlike hot water systems, which gradually get cooler as they move around the circuit, if you maintain the pressure of a steam system, the temperature remains constant. This is our little walk through the steam system. As you can see today, we're going to start off in the boiler house or the powerhouse if you're generating electricity there as well. We'll then go through the distribution system to the heat exchanger, where we're taking the valuable energy out of the steam, through the steam trap, condensate return system, and then recycle back in the hot well or deaerator for use in the boiler again. We have a couple of polls today. I'm going to let Gunther introduce poll number 1.
Okay, we would like to know from you, how is the heat provided to your hospital or to your estate? Please choose as many as apply for you. Is it steam boiler? Is it hot water boiler? Is it CHP, combined heat and power? Or is it decentralized hot water or district heating? You can choose as many as applies for you.
Thanks, Gunther. While we're waiting for those results to come in, I'll talk you through the boiler heat losses. Typically in hospitals, we're using fire tube boilers. This is where we combust the natural gas in a burner, and it flows through a series of tubes in a water bath with the steam evaporating off the top of the boiler. This type of design can use many different types of fuel, including biomass if required. Typically, we're burning hydrocarbons, and primarily in the UK, it's natural gas. The flue gas temperature is both hot, typically between 180 and 200 degrees C, depending on the steam pressure we're using, but also humid. When we burn natural gas, it's CH4, and the products of combustion are CO2 and H2O. The H2O is water vapor going up the stack. I'll talk more about that later. Other factors that increase the heat losses through these boiler flue gases are scaling. Effectively, the boiler is a giant kettle. It's constantly concentrating salts, and like your kettle, it gets covered in scale. This scale inhibits heat transfer, resulting in hotter exhaust gases. Another important area is oxygen trim. We want to maintain just the right amount of excess air to have the ideal combustion within the boiler. I mentioned about the scale formation. As we're continually condensing in the boiler, to maintain TDS, or total dissolved solids, that's the salts that we're concentrating in the boiler, we need to continuously blow down some of the water within the boiler to prevent those concentration levels from getting too high. This blowdown is another type of loss. The boiler itself is physically a large vessel and loses heat from its surface. These shell losses are around 4%, although for boilers that are operating on standby or low fire duty, as a percentage of the total consumption as a fixed amount, then this can increase considerably. How are those results looking, Victoria? Shall I keep going?
I've published the results. I don't know, Gunther, if you want to talk through them.
Yes, okay. So we've got steam boiler with 64%, hot water boilers with 36%, CHP 52%, decentralized hot water 22%, and district heating 14%.
Thank you very much. So we'll now look at how we can recover these heat losses. There are two main strategies to recovering boiler flue losses through economizers. We can have an indirect contact approach where we use a series of tubes and fins. The advantage of this approach is it can produce high hot water to temperatures, typically up to 90 degrees C. This is ideal for hotter, drier exhausts. It also is good for simple designs where you've only got one or maybe two heat sinks. A heat sink is where we're actually using the recovered energy. Direct contact systems come into their own where we have lower temperature heat sinks available, as we do in the hospital environment. They can recover the maximum amount of latent heat from a humid exhaust stream. They're also not susceptible to fouling if you have dirtier sources. I'll talk today a lot about condensing heat recovery. Just give me a second. Burning natural gas, CH4, the products of combustion are H2O and CO2. In the UK, the convention is to rate boiler efficiency on the lower heating value of the fuel, which hides the wet losses available when you condense the exhaust. This is a hangover from burning coal and other dirty fuels, which are designed to operate above the acid dew point. As you can see here, for natural gas, there's a considerable difference between the lower heating value and the higher heating value. If we were to rate up to recover all of the energy from the higher heating value, we get an extra 11.5% of energy out of our fuel. This is a typical heat recovery curve for a gas-fired boiler. This is a 17-ton boiler. As you can see at the bottom part here, we've got a linear increase in energy recovery as we reduce the temperature. This is called sensible heat recovery. Around about 60 degrees C, we reach an inflection point where the heat recovery increases significantly. This is the wet bulb temperature and marks the point where, as we cool the exhaust, we start to get condensation. And this is where we can recover a lot of additional energy through a direct contact condensing heat recovery system. This picture here shows you the installation for this curve. You can see it uses a combination of both an indirect fin tube and a FluAce as a direct contact unit. This is a common configuration, allowing you to boost the temperature of the energy recovered in the FluAce stage to a higher temperature with the indirect stage. We can see the same graph here again. The red area represents the sensible energy, the temperature reduction of the exhaust, and the blue area is the condensing energy, where we get the latent energy released as we condense the water vapor into, the water vapor into water and condense it. This scale on the right-hand side is kilowatts recovered per 100 kilowatts fired. Essentially, it's a percentage. Typical non-condensing economizers can achieve 2 to 3%, reducing the exhaust gases to a maximum of about 120 degrees C. With the Fluway system, we can recover much more heat by moving into that condensing zone. Typically, as a hierarchy of heat recovery, you need to look at the ideal solution being a match between the source available, the exhaust, and the places that you can sink it. If we only have high temperature limited sinks, then we're going to be looking at a non-condensing fin tube. We can also look at condensing with fin tube designs, and we can talk to anyone that's interested about that as a separate topic. And then we have the direct contact condensing Fluways. As I said, this is always going to be the most efficient solution because we're not limited by the heat recovery surface area with a Fluways design, as I'll explain later. This is a typical case study for a condensing heat recovery project installed at the Wigan, Lee and NHS Trust in the UK. Following the success of an earlier project, 3 additional projects were implemented across the trust. At Wigan Hospital, there is an extension to the heating loop of an existing Fluways, including the critical care units, replacing the existing DHW shell and tube heat exchangers and plate heat exchangers. The Wrightington Hospital installed a Fluways heating domestic hot water and heating calorifiers for building heating, and the Lee Hospital installed a Fluways from their 3 medium temperature hot water boilers, preheating the hydronic loop returns. That's the water coming back from the hot water circuit. The overall savings were around £290,000 per year, and since they were installed in 2015, we've saved over 1.4 million in natural gas for the hospital. This was a 34% improvement than the original projected savings for this project. The customer's been very happy with this site, and we were able to manage the installation to minimise the impact of the critical care units where we were operating, and making sure there was sufficient redundancy throughout the work to maintain the operations of the hospital. So this is a Fluways. How does it work? We take the hot air from the boiler, the CHP, whatever the source is, and we draw it up through our heat recovery system. We have a fan which draws the hot air from the existing exhaust stack. This means we're never going to put a back pressure onto your boiler or CHP plant because we're actually sucking the air into our system. If our fan was not running, then the exhaust gases would just continue up the existing stack. We then directly shower cold water through a system of nozzles and showers over some special packing material that provides resident time and contact between the water droplets and the rising exhaust gases. You can get very close approach temperatures. If we have cold water at 10 degrees C coming in here in sufficient volume, we can actually cool the exhaust gases down to around 12 to 15 degrees C. The Fluways can be used to recover energy from a variety of sources: boilers, reciprocating engine CHP plants, gas turbine CHP plants, dryers and waste incinerators. Effectively, what you have with the Fluway system is a hot water heater, giving you 3 hot water to use throughout the hospital, whether that be for HVAC systems for heating of the hospital, radiators in the heating circuits, or even better, domestic hot water and make-up water for the boiler. The colder the water we can bring into the Fluways tower, the more energy that we can recover. We can also use other heat sinks within the hospital, whether there's a swimming pool in the hydrotherapy unit, or catering requirements, laundry requirements, where they're on site in the hospital. Many hospitals, as we saw in our poll, are taking advantage of combined heat and power. CHP systems can generate power for either a reciprocating engine attached to a generator or a gas turbine. And effectively what they're doing is they're making use of the waste heat that's generated as part of the electricity generation process and using it on site. Electrical efficiency is typically 35 to 45%, depending on the size and the operation of the CHP system. Typical installed efficiencies, taking into account the electrical and the thermal heat, is 65 to 75%. With a FLUACE, we can significantly increase these efficiencies, typically achieving over 90% total efficiency. We do this through improved heat recovery from the exhaust gas stack and better integration within the hospital systems. Again, an example of this was a new CHP that was being installed at the Wiston Hospital. We installed the FLUACE there on the CHP system and 2 hot water boilers, and boosted the efficiency of the 1.2 megawatt electric CHP from 75% to 95% total efficiency, with additional savings at winter peak loads, where we were also recovering from 2 4.4 megawatt boilers. Most CHP systems are sized for the base load of the plant and therefore have boilers required to meet the peak loads of the plant and also provide redundancy for the CHP. This is the heat recovery curve here. You can see we're taking heat out of the existing CHP heat recovery systems at just over 100 degrees C, and the dew point here is slightly below. This below what we see in a natural gas-fired boiler due to the additional excess air we have in a CHP system. Here it's just below 50 degrees C. The system recovered from the hot water boilers and the CHP, as I said, delivering that heat to 3 domestic hot water calorifiers and also preheating the hot water hydronic return loop. We now move on to the next stage in our system, the distribution system. Distribution listers typically account for around 10% of the steam produced. Steam is typically distributed at the boiler pressure, which is normally 6 bar, where there's no requirement for higher temperature steam in the system. If there's a laundry or other facility on the site that requires higher temperature steam, it may be as much as 10 bar. The reason we distribute steam at high pressure or relatively high pressure is we then reduce the volume. It's a gas. As we pressurize it, it takes up less volume, so we can use smaller pipe, reducing installation cost and heat losses through reduced surface area. That steam is then reduced at the point of use through a pressure reducing valve and a control valve for the individual heat exchanger. The advantage of this is that it increases the dryness as we reduce the pressure of the steam, and also increases the amount of latent energy. Counterintuitively, with steam, the lower the temperature and pressure that you consume the steam, the more energy per kilogram you get out of it. This is because we're actually using the latent energy rather than the temperature to drive the heat used. What I'd recommend when looking at distribution systems is, rather than considering decentralization across the full site, is to actually look at the steam system with an approach of rationalization, looking at those outliers and redundant sections of the steam distribution system that can be removed simply and effectively. The function of the steam distribution system is to deliver the steam dry to the point of use with no air. The reason we don't want air is a very effective insulator. That's why we use it in the thermos flask double glazing. And compared to the typical heat transfer coefficient for the heat exchanger wall, it's at 1,500 to 3,000 times in terms of its thermal resistance. Water is also an effective barrier to heat transfer when you've got a condensing system of a magnitude of 100 to 150 times. How much this affects the overall temperature in the product is determined by the thickness of those walls or heat transfer barriers. Air not only inhibits heat transfer, it also reduces steam temperature due to partial pressures. What this means is when we mix two gases together, in this case steam and air, the pressure that we read on the pressure gauge is partially contributed by the steam and partially contributed by the air. So we might read 2 bar on the pressure gauge, but we've only got 1.7 bar of actual steam, which has an effect because the steam pressure is related to its temperature on the temperature that we actually receive. This is particularly important in SSD in the sterile services department, where we rely on achieving temperatures to have full sterilization. So removing air from these systems is particularly important. Water entrained in the steam also reduces the heat content proportional to its mass fraction. So if we only have 90% dry steam, it means we're only getting 90% of the energy out of that steam at the point of use in the heat exchanger. So how do we keep our steam dry? We need to make sure that at regular intervals, typically every 30 to 40 meters, we have dirt pockets to allow the condensate that's flowing along the bottom of the pipe to collect and be drained through a steam trap. The function of the dirt pocket is also to prevent and collect any dirt from getting to the steam trap and causing it to malfunction. We also need these dirt pockets before a rise, at the end of any line, at the low points within the steam system, and before any isolation valves, which if they're shut, would effectively create an end of line. The reason that these points are important is if we didn't have a dirt pocket and a steam trap there, then condensate would accumulate, creating additional wetness and also problems with water hammer corrosion. We also recommend that dirt pockets are installed before control valves and pressure reducing valves and any other sensitive valves in the system. This helps maintain their life, make sure they operate correctly, and prevents them from being damaged by erosion. Insulation within the distribution system has one of the fastest return on investments. Damaged insulation can allow water ingress and actually increase the heat losses because you're then actually evaporating off of the pipe. In extreme circumstances, you may even notice that your gas consumption increases on wet days. If you see this within your facility, this is a good indicator that you've got serious water ingress within your system. We now move on to the heat exchanger. The heat exchanger is where we get the useful heat output from the energy we've burnt in the boiler. There are two main designs of heat exchanger: plate heat exchangers and shell and tube heat exchangers. Plate heat exchangers have a very high surface area, which makes them compact and have high heat transfer rates. They also have very low volumes, which means that they're responsive to changes in demand, and also therefore don't require any annual pressure tests. They can, however, be susceptible to leaks due to the number of seals between all the plates, and also to blockages if you've got debris or scaling within the steam or hot water due to the small diameter flow paths. On heat recovery systems, the economic approach temperature is much lower, which can significantly increase the recovery for heat potential for heat recovery compared to a shell and tube heat exchanger. If we use brazed plate heat exchangers or welded plate heat exchangers, that eliminates the gasket leak problems, and they're very suitable for steam applications. One thing to bear in mind when specifying plate heat exchangers is that increasing the pressure drop across the heat exchanger can significantly reduce the cost of the heat exchanger and also improve its heat transfer potential by having more turbulent flows. Shell and tube heat exchangers are the traditional design. They're very robust, can cope with suspended solids, are very resistant to leaks. They do have higher heat losses and a bigger footprint within your plant. We now move on to the steam trap. As I mentioned earlier, when we're using steam, we are taking the energy from the phase change of steam to condensate. That means that once the energy has been given up, the steam turns into water and we need to discharge it. In fact, in most other languages, the steam trap is more correctly called a condensate drain. These steam traps are traditionally mechanical devices operating on a variety of different principles. Some operate on temperature, opening and closing on temperature. Others operate on density with various float mechanisms. This one here is an inverted bucket trap, which again is a density trap. Effectively, you have a bucket that moves up and down when steam and condensate is present. We also have thermodynamic types of steam traps, where the trap opens and closes based on the difference in flow velocity between steam and water through the device. The problem with these mechanical steam traps is that these opening and closing devices are operating several times a minute in hot, dirty environments, many thousands of times a year. That contributes to a 5 to 10% annual failure rate. When these steam traps fail, they either fail closed, inhibiting heat transfer, or fail open, wasting valuable live steam which hasn't condensed and contributed any useful energy to the system, allowing it to escape out of the system. There is a solution. The GEM trap is a permanent solution to steam trapping. It has no moving parts. Its performance guaranteed for 10 years. It's very easy to maintain. Full maintenance can be conducted in line within 5 minutes, as long as isolation can be achieved, and there's no or minimal requirement for spare parts. It's also been demonstrated both in field testing and laboratory testing to be more efficient than most mechanical steam trap designs. Here we have an example of a case study, again at the Wigan and Leigh Hospital. They replaced 260 mechanical steam traps, saving £85,000 per hour. One of the biggest advantages that Mark Hogan, the environmental manager, saw was the elimination of the requirement of spare parts and replacement traps and the associated maintenance costs. So how do the GEM traps realise these savings? On this graph here, we have energy consumption on the left-hand side, and then on the x-axis, we have time. At any point in time, the energy consumption of your plant slowly increases as the performance of the mechanical steam traps deteriorates. Until such a point, you do a steam trap survey, identify the worst actors, the failed traps, and replace them. You can then reduce the steam consumption. But of course, no sooner have you done that, steam traps start to fail elsewhere within the plant, and we are trapped in this constant fail-replace cycle. If we were to conduct more frequent steam trap surveys and replacements, then we just have more smaller peaks. This does result in energy saving, but also increases the maintenance costs. The first area that the GEM traps realise energy savings is they eliminate this steam loss through failed traps. We can also demonstrate, as I said earlier, that the GEM trap is more efficient than fully functioning mechanical steam traps, resulting in a saving. This saving is then performance guaranteed for the life of the steam trap. If you want to know where the steam goes, it's lost out the vent. This is a hospital vent before and after GEM traps were installed throughout the facility. We now move on to the condensate return system. Once we've condensed the steam into hot water, 20% of the energy is still contained in the condensate. Roughly half of that as we release that 180 degrees condensate across the steam trap, a portion of it re-evaporates. We have 3 options for our condensate return systems. One is to discharge to drain, where we get total loss of all energy and treated water. This is very uncommon in the UK due to high energy costs. We have a vented return system, which reuses the condensate, reducing water treatment costs, and we also get the sensible heat content of the condensate. We can also look at pressurized return systems. They reuse the condensate, the sensible heat, and also recover the flash steam. Flash steam recovery is a great opportunity for many sectors. What we need to go through is this checklist to make sure whether it's suitable for your plant. We need a low pressure steam consumer. We need to be able to effectively separate low pressure and variable pressure processes, those with control valves, from the condensate return system that feeds to the flash vessel. We also need a similar demand between the generation of flash steam and the consumption of low pressure steam. Ideally, that's located close to the high pressure system, to the flash vessel, because low pressure steam has a very high volume and therefore needs large pipes, large diameter pipes to transport it. In the hospital environment, most of our steam is actually being used for generating hot water, which reduces the opportunity for flash steam recovery. We then return finally to the hot well or deaerator. This is where the hot water is returned and stored for use in the boiler. As I said earlier in our presentation, boilers operate as giant kettles concentrating salts. Water treatment is essential to maintain the safe operation of boiler plants. This is traditionally done through the adding of phosphates as a sludge conditioner to prevent scale formation. Effectively just create a different type of scale that doesn't adhere to the tubes, that falls off and drops to the bottom of the boiler, and sulfates to act as an oxygen scavenger and prevent corrosion. Both of these chemicals add to the total TDS, the total dissolved solids within the boiler, increasing the amount of blowdown required. An alternative is a filming amine treatment, such as supplied by GemChem. These filming amine water treatments have several benefits. First of all, it's a pure liquid, so it doesn't add to the TDS at all, reducing the amount of boiler blowdown. Energy savings can be realised between 3 and 5%, depending on the existing blowdown level. The actual cetamine itself is volatile. That means that it evaporates out of the boiler with the steam, travels around your steam system, providing protection for the steam and condensate system. It forms a single molecule thick layer, providing corrosion protection and descaling. This cetamine treatment is robust and will even continue to protect the system when it's shut down or overnight and weekends. Recently, we were challenged by Southmead Hospital, who were struggling with iron levels within their system to prove the effectiveness of this treatment over 6 months. You can see here the condensate samples collected from the 3 boilers and the condensate return before the for the feed water. There's a clear sample. The 3 boilers before the treatment was started, and then visually you can already see the difference. Here we can see the iron level in parts per million. You can see a rapid drop following the GemChem treatment being started across the feed water, all 3 boilers, and the condensate return. The hospital are very, very happy with this and have continued the treatment program. I'd now like to take you in a slightly different direction to look at how we can achieve pollution control with heat recovery. Now it's time for our second poll. Gunther, I'll ask you again to introduce it, please.
Yeah, so we would like to know from you whether reducing NOx emissions from your estate operations is a target for your facility. Can you please answer with yes or no?
Thank you, Gunther. So why is NOx emissions important? Many NHS hospitals are located in inner city areas which frequently don't meet the European air quality standards. Air pollution is linked to many killer conditions such as heart disease, stroke and lung cancer, and contributes to around 36,000 additional deaths annually. A recent study by King's College in London, looking at 9 English cities, demonstrated that on high pollution days, there are 673 additional out-of-hospital cardiac arrests and hospital admissions for stroke and asthma. with associated spikes in ambulance and 999 call-outs. In Britain alone, known NO2 emissions have been estimated to kill 23,500 additional people every year. In London, and this is where some of you will probably recognise this map, we can see the NOx emissions in different areas of the city. In London, in 2018, the total annual quota for European NOx limits were exceeded in January that year. There's still 11 months of more NOx emissions for the poor people that live in London. You can see here the yellow and above and darker colours are areas where the objectives were not achieved according to the European targets within London. How are the results coming back from that poll?
So the results are 60% said yes and 40% no. That's interesting.
Thank you very much for that. We've talked so far about the fluace. Many of you may recognise that the fluace is essentially a scrubber, and a scrubber is a technology that's used for removing particulate emissions and acidic gases from exhausts to control pollution. The fluace is optimised for energy recovery instead, but we still retain many of the pollution control advantages. In one of your handouts for today's session, there was a paper between Johnson Controls, Thermal Energy International, and a Canadian hospital studying the effects of adding a fluace to both a natural gas-fired and number two fuel oil or diesel-fired boiler. You can see a significant reduction in particulate matter and proportional reductions in the in all of the exhaust gases due to the savings through burning less fuel. Thermal NOx occurs in combustion processes where the flame temperature is above 1300 degrees C. This is the highest temperature part of the flame. Many NOx combustion strategies to reduce NOx involve increasing the thermal mass of the combustion air by recirculating exhaust gases. Effectively, by recirculating these inert gases, they add more combustion gases and lower the flame temperature. The problem with this strategy is it can reduce the capacity of the boiler because you're now putting inert gases through it by 10 to 25%, and you're also heating those inert gases, which reduces the overall thermal efficiency of the boiler whilst trying to meet the NOx limits. The Eco Low NOx takes an alternative strategy. Instead, it humidifies the combustion air through a preheating evaporator and completely saturates it. This additional water in the combustion air increases the specific heat capacity of the combustion gases, significantly lowering the flame temperature and achieving NOx reduction. As we do this, we're also preheating the combustion air, meaning that heating doesn't have to be completed by the burner, increasing the efficiency of the overall system by typically 3%. As you've seen earlier on in the presentation, we have a fluace on this side of the Econo Low NOx system, and by adding additional heat sinks, we can further increase the heat recoverable. Another advantage for heat recovery of humidifying the combustion air is you increase the dew point or the temperature that we can recover in the fluace section. This system is suitable for retrofit or new build applications. Here we can see we have the burner, which is the heating the boiler, and then the exhaust gases. Again, we have the shower, allowing us to heat the water and condense the exhaust gases, and we get warm water coming out of the bottom of the fluace. This is typically heated to 63 degrees C. It's around 5 degrees C higher than a typical natural gas boiler. The 63 degrees water is then passed through an evaporator, which is effectively operating in the opposite way of the fluace, to heat and humidify the incoming combustion air. And this is heated from 20 degrees C in the boiler plant to around about 55 degrees C going into the boiler. We have an example of the application of this technology from the US and New Jersey at the Helen Ford Hospital. An expansion to the 587-bed hospital following the relocation of a campus required additional heat to meet the operating needs of the hospital. Initially, the option to add a fourth boiler was considered, which would have cost $800,000 and increased CO2 and NOx emissions, which they're already at the limit at for the site. Additional constraints, the limited space available to install the new equipment within the existing hospital power plant. The solution that they settled on was to install an Econo low NOx system, including the condenser and evaporator as I've just described, as part of a retrofit. They were installed in the place of an old incinerator plant. It was relatively simple to connect the 3 existing boilers, with only 400 square feet of footprint required for the installation. Following installation, the boiler combustion plant efficiency was increased from 80% to near 100%, resulting in 25% fuel savings. These savings were effectively allowed them to heat areas of the hospital for free and negated the requirement for the additional boiler, resulting in a 30-month payback return on investment. Here are the results in terms of the NOx emissions on boiler 2. You can see that the NOx emissions depend on whether you're at low fire, medium fire or high fire. And across all of those commissions, there's a significant reduction in NOx emissions from around 63 parts per million to 70 parts per million prior to the Econo low NOx being installed. Following the installation of the Econo low NOx, they vary from 12 parts per million to 22 parts per million. Overall, this is a reduction in NOx emissions of 74%. It's clear that that across the whole country, NOx emissions and air quality are becoming much more important in the agenda for healthcare estates. I've even seen it hypothesized recently that particulate emissions and smog created by NOx can even increase the transmission of COVID-19. I'd like to thank you all today for your attendance. I hope you found it useful. You have both mine and Gunther's contact details here. We're happy to take questions now, along with Walton, who's been intimately involved in many of these projects that I've described. Or alternatively, you can feel free to contact us privately, as Victoria said, in your own time.
So thank you very much. Thank you very much for your presentation. As Sam said, if you have questions for our speakers, please do put them into the questions function now. And while you folk are doing that, just a reminder to visit the Healthcare Estates website, healthcareestates.com. We have other webinars running in coming weeks. We have quite a few on-demand webinars that you can watch as well. So please do put your questions into the system. We do have one from Tom Roberts. So Tom says, you were talking about dirty steam. How does the GEM trap stop from blocking with dirt?
The GEM traps has a 3-stage protection mechanism to try and eliminate debris from the system. So most of the debris in the steam system is normally products of iron corrosion, and typically magnetite, which is what happens when you corrode iron in the absence of oxygen. As magnetite suggests, it's strongly magnetic. So we have a 3-stage protection system. First of all, we have a filter basket to take out the majority of the debris, and any fine particles that get through the filter basket are attracted to the magnet and then unable to affect the steam trap. You'll see a similar system in many hot water heating systems. They use magnets to prevent the products of iron flaring up those systems as well. Additionally, the steam trap has an inverted cone entrance to the orifice, which prevents any ingress of hydrocarbon or coagulation of small particles, causing them to settle together and block the trap. Typically, we find that blockage rates are similar to mechanical steam traps. We run a number of service contracts for our NHS customers where we take responsibility for all the servicing. So we have first-hand experience of the blockaging because that's included within our contract for the hospital to clean them and keep them operating effectively.
So Tom has a supplementary question, which I'll address now. He says, thank you. How often does that have to be emptied? Can you do it online or do you need to take it offline?
We've designed our steam traps for line drainage traps and small duty applications, and they're the ones that have the smallest orifice within the trap because there's only a very limited amount of condensate. And they're fully designed to be maintained in line, as I said, typically around 5 minutes, as long as you can isolate the system. You can fully maintain those traps.
Super. So I've got a question from Tim Gray now, and I apologise if I get any pronunciations wrong on some of this technology. So Tim says, have you considered the Ecolinox technology for use in conjunction with reciprocating gas engine NOx reduction in place or in combination with SCR?
It's not something we've looked at the moment. I don't know if that's something that you would be interested in doing, but reciprocating engines are obviously a lot more complicated in terms of humidifying the exhaust gases, and we work with a reciprocating engine supplier to make sure that they were happy with humidifying the combustion gases. I don't know, Walton, if you've got anything to add on that.
We did do some very small trials on it some years ago, and certainly we would be delighted to work with some of the reciprocating engine manufacturers to do some larger trials on that very thing. It probably will work, it definitely will work, and it may even reduce the need for such a large catalytic converter. Thank you.
If I can just interject for one moment, because I think we still owe Tom an answer for his question, the previous question, how often do you need to look into the traps regarding the blockages? We recommend once a year.
Excellent. Thank you. So next question is from Peter Covington. He's asking, are gem trap sets suitable for process loads? Does condensate tend to back up?
Yes, so the gem traps are suitable for process loads, and it's maybe a little bit more of an in-depth explanation than we have time for today, but I'll be happy to pick up talking through their operating principles, and also particularly when you're looking at process loads, we normally have a control valve which significantly increases the operating range of the gem trap because it's changing the pressure within the heat exchanger. But yeah, we have very good experience with a number of hospitals and most industrial processes. There are very few, I'd say less than 1% of applications that we come across that are not suitable for gem traps, and obviously where they are, we'd highlight them, but I can't really think of any off the top of my head that we've ever come across in a hospital.
Okay, we don't have any further questions. It might be that there are questions that will come to you privately, which is absolutely fine. So as we come to the end of the hour, thank you again to our speakers, Gunther Lang, Sam Morby, Walton Dunlop from Thermal Energy International, and thank you to everybody for watching today.
Thank you for attending and thank you for organising, Victoria.
You're
Thank you
welcome.
very much, everybody.